Jumbo. We're starting the second phase of our first chemistry section, and most of this stuff should be new to you. So hopefully you can pay attention. Hopefully I'll make it somewhat coherent. This is a nuclear chemistry notes. This means we're looking at what's going on in the nucleus of an atom. We've talked about electrons on the outside of the atom, and generally they're fairly loosely held. They can be lost or gained, and that's what we have in chemical reactions. The nucleus is an insane part of the atom, incredibly dense, and you have protons and neutrons basically glued together. Now the protons all have a positive charge, and so they want to actually move away from each other, repel. And so physicists said, but they don't, so we need a clever name for the force that holds it together. And the force that holds together the nucleus is cleverly called the strong force. So we're looking at what happens when we do things to the nucleus and overcome that strong force. So that's why the first thing is nuclear chemistry is the nucleus of an atom. We've talked about the protons and neutrons live in the nucleus, and overall the protons give a nucleus a positive charge. This is not a new definition, and it still applies here. We're looking at isotopes. Iso the same, so same element, same number of protons. What's different? Different masses, therefore different number of neutrons. We're going to look at things called nuclear symbols, and they're very straightforward. And we have three examples of nuclear symbols looking at different isotopes of carbon. So we have carbon 12, carbon 13, carbon 14. You write the element symbol down the usual way from the periodic table, and now on the upper left you put the mass of the particle, and lower left you put the nuclear charge. And for any element, that's simply its atomic number. That's saying, hey, how many protons are there? And so we say, oh, 6 protons, 6 neutrons, that totals 12. So that's why there's a 12 for a mass number. All these things across the bottom are 6 because they all have 6 protons. And each isotope we've gone up by 1. So 7 neutrons, 8 neutrons, adding to the mass. That's fairly easy. There's something called radioactivity, and that just means we're looking at nuclei that are unstable. Some nuclei are stable, some isotopes, and other nuclei are unstable. If you have a stable nucleus, that means it doesn't want to change, then it would be considered not radioactive. If you have an unstable nucleus, then it's radioactive. It's going to give off energy in some form. And so we have things called alpha particles, beta particles, or gamma rays. Now, why would it be unstable? Well, it turns out there's a sweet spot for having the right ratio of neutrons to protons. If you have too few neutrons or too many, you're going to have a radioactive isotope, and it's going to change and do interesting things. So that's what we're talking about here. Some isotopes are stable, radioactive, and some are unstable and called radioactive. So if we're looking at smaller elements, the ratio is typically 1 to 1. So if you look at something like nitrogen, nitrogen 14 happens to be stable, 7 protons, 7 neutrons, you're looking at a 1 to 1 ratio. When you get up to things like gold, plutonium, what are things, platinum, some of these big things, if you're going to find a stable isotope of it, usually it's a 3 to 2 or 1.5 to 1 ratio of neutrons to protons. I should be running out of real estate there. Okay, let's see if there's anything on the back here. Now we go to half-life, and every year I ask students what's the definition of half-life, and every year a lot of students give me absolute malarkey, stuff that doesn't make sense. So the symbol for it is a little t for time, and then 1/2. When we're looking at half-life, this applies to radioactive isotopes, things that are going to break down or decay over time. So we have a definition. You should know it. Half-life is the time it takes for 1/2 of the nuclei of a radioactive sample to decay. So let's say I have a radioactive element, and I've got 1,000 grams of it. I would simply record the time it takes to get down to 500 grams. And let's say that's 1 hour. Then after 2 hours or 1 more hour, I'll go from 500 to 250, and then I'll drop to 125. Now, typically when we're looking at samples, we're not talking about thousands. We're going to be talking about millions and millions and millions of particles, because these particles are so tiny. And when you see the word decay here, decay just means break down. Well, a lot of times students can't relate to things called isotopes. It's easier to relate to the chocolate chip cookies. And it turned out, after careful study, that the half-life for chocolate chip cookies is 1 hour. So we're going to say we're just going to start our time. We're just going to declare it 1 hour just because that's the way the graph kind of worked out. Normally when you go on in chemistry and physics, you'd start at time 0. And we say, hey, at time 1 we have 64. And so at 2 hours, we've dropped by a half because we've gone 1 hour from then. So we've half as many, 32. Now you might think that when we go 1 more hour, they're all gone, but that's not how it works. After another hour, we're going to lose half of 32. That's 16. Another hour, we're going to lose half of 16, which is 8. And then 4. And cleverly 2. And 1. And then we're in a bit of trouble. Now we start with small numbers that are nice and easy to plot. Of course, I've said we would have huge, huge, huge numbers. In fact, we would never get to 0. Well, except with cookies. Now you say, how does this cookie example make sense? Well, let's say I made a batch, and they're actually a decent batch of cookies, and there are 64 around. It's pretty easy for someone to go and steal 32 of them, and you still have a lot left. But if someone comes along and tries to steal 32 again, not so good. They're all gone. You have to answer for that. And then, of course, when you get down to 1, it's not worth taking 1 cookie, because then you've got to do all the cleanup or hide the bin or the box or whatever it was. So here's our graph, and this is called the decay curve. So we've just taken it and we've gone, hey, 64, 32, 16, 8, 4, 2, and 1. And this is what we'd see, this kind of pattern for when a radioactive sample is decaying. And what else we got there? Cleverly, it tells you it's not a straight line. That's fairly obvious. So if we look at a question like this, if you had 40,000 grams of radioactive material, half-life is 500 years, we're just going to drop by half each time. So for 40,000 grams, we're going to have 20,000 grams left after 500 years. That's 1 half-life. Now we're down 20,000, half of that's 10,000. So we're only going to have 10,000 left after 1,000. Then we'll drop down to 5,000 after 1,500 years. And then 2,500, and then 1,250. So hopefully that's making sense. And if your math skills are half decent, there's a nice little formula. You can take your starting number, in this case 40,000, and you multiply it by half to the power of how many half-lives. So if you go through 1, 2, 3, 4, 5, you'd go half to the 5th, and you could go 40,000 times half to the 5th power, and you get 1,250 grams if you're trying to do it elegantly. And that would generate basically the same kind of curve that you saw in our chocolate chip cookie graph. So that's it for round 1 of notes, I believe, and we will carry on.